Hi all. Little bit some of the problems with Spring that I didn't cover Saturday. I would like to go over now. Um, springs are such they obey the following law. So if you have oops, a spring that is relaxed, in case you compressed, and you compressed of a certain distance del x, the force The force responsible for this compression is given by a constant called spring constant time the amount of spring that has been compressed. Now, what is the work done by this force? Or in other words, what is the energy used to do this compression? So the energy, or in other words, the work done to compress the spring, as we saw also last Saturday, is equal to half the spring constant times del x squared. And this expression, it can either be used in case you are compressing a spring or you are stretching it. So the potential or the amount of energy to do that type of work is basically the same. So let's take a look in this situation, problem number 8. So we have a block that is moving with a certain speed. There is no friction, so there is no work or dissipative work done by friction. And it goes towards the spring, and after the block collides with the spring is compressed to this distance. So make sure you have all your units in meters. What is the speed of the block when it has moved so that the spring is compressed only one half of the maximum distance? So it's talking about maximum distance. So given the speed of the block, let me try to redo this problem here. So the spring is going to be compressed to a maximum position, and you could call, here's the spring relax, and you could call this distance here del x. Okay, that's the maximum possible compression. So it means when the block was about to hit the spring, the block had an energy, a kinetic energy, and we call this position or this situation, this configuration A. And when the spring is totally compressed, we call that situation or configuration B. And then you list out all energies that happen to be involved from point A to point B. So you go to build a table with all these possible energies. So let's start with kinetic energy. So in position A, does the block have kinetic energy? Yes. What is the value? Half mv squared. And at point B, does it have any kinetic energy? Well, when the block hits position B, the block's not moving because it stops. So kinetic energy is 0. Now, how about spring potential energy? Does the spring have any compressed or stretched potential energy at part A? No, it is relaxed. But at part B, it does have half k del x squared. So from here, the information you can get is the value of your spring constant because the total energy is not lost anywhere. So we have a certain amount of energy at part A, and that energy appears in part B as a compressed spring. So in other words, the energy in configuration A must be equal energy in configuration B, or half m va square is equal to half k del x squared. So look at this. The speed is given and the mass is given. So we have the kinetic energy. and the maximum compression is given, which means we can solve for K. Now that you can solve for K, the problem is asking you what is the speed of the block when it was halfway into the compression. So we are talking about, in fact, a configuration C. So a configuration C, it has not only kinetic energy but also potential energy involved. So you can open up another configuration and call C, and then say, okay, what is the kinetic energy at point C? I don't know, but it's mass and VC squared, and we want to find that speed, right? And does it have any potential energy? Yes, it does. It's half K, which we calculate, right? K is calculated, times half of the maximum compression square, which is 0.68 over 2 square. And then you can solve for the speed, right? You can take, okay, the total energy at A is equal to total energy at C. Or you can say total energy in B is equal to total energy in C, right? Because A and B are the same. Okay. See if there is another question with spring. This one. So we have a block that's right here, and is held in place against a spring by a 75 newtons horizontal external force. So which means you take a block and you compress this spring with a force that is 74 newton, right? 74 newton. And which implies that your spring has been compressed by a certain amount of X. So what is interesting is that we know force is equal K times the amount of spring that has been compressed. So we have K del X. Okay. So I'm just reading the problem. The external force is removed. So now you take this external force and take it away. The block descends. So once you take that force away, the spring is all get, open up. And the spring is pretty much sending this block away. And the block descends a ramp and has a velocity that is given. What? Oh, no. When the external force is removed, the block comes out with this velocity of 1.2 meters per second. And the blocks descend a ramp, and of course at the lower end has a little bit more of speed. The track is frictionless between point A and B, and the blocks enters a rough section. The coefficient of kinetic friction is given, and the velocity at point 3 is 1.4 meters per second. The block moves on D where it stops. The initial compression of the spring is close to. So this problem here, it wants to find the initial compression of the spring. So we want to find Kx. So one of the given information, this problem seems to have too much information we don't need. So we want to find x, right? And it is said the block's projected with an initial velocity given by that. So let's take the situation of the block compressing the spring that way, and we call that configuration A. Configuration B is when the block is about to leave the spring, right? And then we can say that total energy that is stored in the spring when the spring is itself compressed is converted into kinetic energy and the block moves. In other words, if we do that little table of energy, configuration A, configuration B, and then we write down kinetic energy at A is 0. Block's not moving. At B, we have half mass of the block, which we have 1.37 kilograms times V1 squared, which is 1.2 meters per second. We have the mass. And how about spring energy? Well, at A, I do have half K del X squared. And at point B, I don't have it. So those are the only two energies that play any difference on the motion of this block. And then we can say total energy at A is equal to total energy at point B, or half K del X squared is equal to half M V1 squared. Well, here's the problem. We want to find the initial compression, right? We don't know K and del X, but we have K, a ratio of K and del X here. So we could take K out of this expression, plug it in here, and then we could find our stretching del X. Okay. And the last one is the problem number 13. We have a block, 2.5 kilograms, that slides on a rough horizontal surface. So we have friction. And since we have friction, there are dissipative forces at play. So if you do a free body diagram on this block, what are the forces on it? We have the weight. We have the normal force acting on it. See, the spring exerts a force from right to left, calling this force of spring. And since the block is moving to the right, and since the surface is a rough one, there is also a frictional force to the left. Both of these forces, not only spring, but friction, they contribute to slow down the motion of this block. So this block has a speed of 1.2 meters per second when it makes contact with a spring. Okay, the block comes to a momentary halt when the compression of the spring is 5 centimeters. So the maximum compression is 5 centimeters, 0.05 meters. Don't forget to convert that to meters. The work done by friction from the instant the blocks make contact with the spring until it comes so this is the work done by the spring. What is the spring constant? So we want to find K. We want to solve for K. So again, we build our energy table, and we have the following configuration. Configuration A is when the block is about to touch the spring. Configuration B is when the spring is totally compressed and has reached the maximum compression, right? So part A, what do we got? We have kinetic energy. And we know the value because we know the mass of the block, we know the speed in which it goes, we have the kinetic energy. Kinetic energy at part B is 0, since the block is not moving. It's given by half m speed squared, and the speed is 0. So here's kinetic energy. How about spring potential energy? At A is 0 because the spring is relaxed. The spring is not compressed or stretched. But at point B, the spring is totally compressed. And then we can write the expression for the work done by the spring. Half K, which the spring constant's what we want to find, by the way. What is the spring constant? That's what we want to find. And del X is the maximum compression, which is 5 centimeters, or 0.05 meters is right here. Okay. So what else do you have to include? Remember, we have the friction doing some work. So the friction in our book, it is called work done by other forces, by forces other than gravity, or forces other than the spring, or forces other than the torque that rotates. And we are going to learn this later. So when you add the work done by other forces, you have to consider if the external forces you are considering, they do a positive work, which means they contribute to increase the speed of your system, or they slow down your system if they contributed to have your mobile, your car or bike, to slow down. So the work done by others in this case is given, is a negative number, and then you plug it in there. So to find your K now is a matter of adding up all these factors. Energy at point A, energy at point B. See, the procedure is always the same. You go, you establish a configuration, a position, and as far as the system develops, and then you outline all energy involved, and then you add them up, and then you can find and solve for unknowns. What is the coefficient of kinetic friction between the box and the rough surface? Well, we want to find the coefficient of kinetic friction. And we know that friction force is equal to the coefficient of kinetic friction times the normal force. In this case, the normal force is the weight of that block. Since all, wait a second. Oh, just a second. Okay, wait a second.